Data sheets and properties of plastics are very important from the processing aspect also. There are two types of data sheets that are of prime importance to us. The first one is a property data sheet, and the second one is a processing data sheet. So it's very important that you always look at units. There are three types of units typically used in injection molding. One is the SI system, second is the English system, and the third is the metric system. The SI system is mainly used in research work in injection molding. The English system and the metric system are much more commonly used in production environment. Here is a data sheet, which is the properties data sheet for a Cycolac ABS material. You can see it gives you mechanical properties, impact properties, thermal properties, and so on. And again, these are more important for designers. However, for us as processing people, the three properties that are important to us is the specific gravity, shrinkage, and melt flow rate. And I'll talk about these things here very soon. Also notice that in data sheets, you have a value, you have a unit, and you also have a standard of testing. For example, the mechanical properties have been tested by using the methods of ASTM D638. So also when you're comparing data sheets, not only compare the units, but also compare the testing methods. So that was the first type of data sheets, which is the properties data sheet. Now we go to the second data sheet, which is the processing data sheet. And again, this is for the Cycolac ABS from SABIC. So this gives you drying temperatures, drying times, cumulative drying times. Very soon we'll talk about what cumulative drying times mean. The moisture content, melt temperatures, mold temperatures, and so on. It also gives you this data: back pressure values, screw speeds, short size to cylinder, and vent depth. And you can see that there are some numbers here. I've got a red box around this and question marks here because there is some of this information that I do not agree with, and one has to be very careful when using this data. And again, I will show you what I mean by that. And again, we will discuss this in the class as we move forward. But for now, just keep this in mind that these values should be used very, very carefully. And here's an example of polyethylene. But if you look at this data sheet, first thing it gives you is these fabrication conditions. They have molded these parts at these conditions. But for somebody who is not very conversant with injection molding, looks at this data sheet, he's going to say, because this data sheet says that I have to use a barrel temperature of 374 degrees, I'm going to use an exact melt temperature of 374 degrees. Or because here it says cycle time is 200 seconds. 200 seconds is a long cycle time. So if they look at this, they're going to get misled by saying that the cycle time should be 200 seconds, or the fill time should be 1 second, or the holding time should be 5 seconds. So it can mislead people because it says here fabrication conditions for injection molding. Also, there's another disclaimer. It says typical values not to be construed as specifications. Users should confirm results with their own test. This is a very important disclaimer that they give you, which tells us that basically these values, again, do not really trust them, go do your own studies, and which again does not make a whole lot of sense. And therefore you need to be very careful with data sheets. So I mentioned that there are three properties in there that are very important to us. The first one is the density. So what is density? Density of a material is a measure of the mass per unit volume and is generally expressed as grams per centimeter cube. That means if I have a cube here and it is made out of HDPE, if it's molded out of HDPE, then this 1 centimeter by 1 centimeter by 1 centimeter cube is now going to weigh exactly 0.95 grams. And therefore we say this 0.95 grams per centimeter cube. If this cube is now molded out of GPPS, general purpose polystyrene, then this cube is going to weigh 1.06 grams per centimeter cube. Or if it's molded, let's say out of PTFE, then the same cube is going to weigh 2.17. See? So as you start changing the material, the weight also changes. If the same cube is now made out of steel, then it is going to be much heavier, and it could be about 7.8 grams depending upon the grade of steel that's used. So it's the same volume, but it weighs differently. Or to explain this in a different way, I've got 4 buckets. They all contain different materials in there. The first one contains helium, which is a gas. It is very light. In the second bucket, you've got styrofoam. Styrofoam is the material that we use for packaging, also called thermocol in some countries. The third bucket, you've got plastic, solid plastic, and the fourth bucket, you've got metal. So if you look at this, it's the same bucket, but now because it is now containing different materials in there, the weight keeps on increasing or the weight keeps on changing. So density is how close the molecules are packed together. The closer the molecules are, the more arranged the molecules are, the more packed they are, and therefore higher is the density, and therefore the weight increases. In some data sheets, you'll see the term specific gravity and you will not see the term density. Specific gravity is nothing but the ratio of the density of the material to the density of water. So if this cube is made out of water, just visualize it. If this cube is made out of water, then this is going to weigh exactly 1 gram. So we say the density of water is 1.00 grams per centimeter cube. We are lucky with this number because it's exactly equal to 1. And therefore now if you see, specific gravity is the ratio of the density of the material to the density of water. Since the density of water is 1, it just simply makes it easy for us. How heavy is polystyrene compared to water? It's 1.06 divided by 1, which is 1.06. So specific gravity is a ratio of the density of the material to the density of water. Luckily, density of water is exactly 1 grams per centimeter cube. And therefore, if you look at specific gravity of polystyrene, it is 1.06 divided by 1, which is 1.06. It's a ratio. It does not have any units. So in the data sheets, you're given density or you're given specific gravity. Numerically, they're the same numbers, but one has a unit and the other one does not have a unit. So why is this density and this specific gravity important to us? That's because barrel shot sizes are always specified in terms of polystyrene. So if you look at the specification sheet for a molding machine, you will see the value for the maximum shot size. The maximum shot size is defined as the maximum amount of polystyrene the barrel can hold when the screw is in the completely retracted position. How much polystyrene can fit in this open space? That is what is called as the maximum shot size. So now that is the maximum shot size in polystyrene. So if I say that the shot capacity of the molding machine is 100 grams, that means the amount of plastic that's sitting in front of the screw here is 100 grams. But if I am now processing different materials, this amount will change. Let us look at this a little further. If the published value of the shot size is 100 grams, that means the maximum amount of polystyrene this barrel can hold is 100 grams. Polystyrene has a density of 1.06. However, if I am now molding nylon that has got a density of 1.15, and now since the density of nylon is 1.15 is greater than 1.06, the amount of plastic that it can hold or the weight of the plastic that it can hold is now also higher, and now that is 108 grams. If I go to acetal that has got a specific gravity of 1.42, the shot capacity goes up to 134. If I go to a 30% glass fill polyester with a specific gravity of 1.53, then the shot capacity goes to 144. So as the specific gravity changes, or in this case increases, the shot capacity also increases. Now look at this. where I'm looking at low density polyethylene and polypropylene, both of which have got densities lower than the general purpose polystyrene. Now, because at 1.06 I can hold 100 grams, at 0.92 I can hold only 87 grams, or at 0.9 I can hold only 85 grams. Which means that although the specified shot size for the barrel is 100 grams, one can never mold 100 grams of polyethylenes or polypropylenes in this barrel. Let us understand this with an example. A very important note here is one should never use 100% of the shot size. The example below that I'm giving you is for understanding purposes only, but please remember that you should never use 100% of the shot size. Now, what is the accepted percentage range? This we will be discussing in further classes, but for now, it's very important that you understand that never use 100% of the shot size. So consider that we have a molding machine with a maximum shot capacity of 100 grams. That means 100 grams of polystyrene is what this barrel can hold at its maximum limit. Now, if you have a mold, let's say it's mold A, and you're molding these parts out of polystyrene, and if the weight of the parts plus the runner is all 100 grams, then in theory, you can run this mold in this machine, because the parts here are molded out of polystyrene and this barrel capacity is in polystyrene. Now you've got a second mold that molds polypropylene. It's mold B. These are completely different parts, and the weight of the parts plus the runner is, let's say, 100 grams. Now, although this is 100 grams, but this is polypropylene with a density of 0.9 grams per centimeter cube. Because the density of polypropylene is 0.90 grams per centimeter cube, which is less than the 1.06 of polystyrene, now the maximum amount of plastic that can be held in this barrel is not going to be 100 grams. It's going to be less than 100 grams. And therefore, you're not going to be able to mold these parts in this barrel. Parts from mold A can be molded in this machine, but the parts from mold B will either have short shots and or will have sink if you try to mold these parts in this machine. And that's all to do with the understanding of the density of the two materials. And therefore, you must always convert the maximum shot capacity of the molding machine into the shot capacity based on the material that you will be molding on that machine. So how do you convert a shot size from polystyrene to other materials? The formula is actually very simple. To convert a polystyrene shot weight to a new material, use the following formula. The new shot size is equal to the old shot size, or the shot size in polystyrene, multiplied by the ratio of the new density to the old density, which in this case is 1.06. As an example, if the published value of the barrel capacity is 150 grams, and now if you're molding a material such as a polyester, a PBT with a density of 1.30 grams per centimeter cube, then the new barrel capacity is going to be 150 multiplied by 1.30 divided by 1.06, which is going to be the new shot capacity for the barrel in this new material, which is now the PBT material.